Hello, everyone. We welcome you to the third episode of the Scientific Saturday Lecture. Our guest for today is Professor Somak Raychaudhury, Director of the Inter-University Center for Astronomy and Astrophysics, also known as IUCA Pune. He has had an illustrious scientific career and has been associated with some of the leading institutions across the globe, including Oxford University, University of Cambridge, and many more. He has made outstanding contributions in stellar mass black holes and supermassive black holes. His work includes gravitational lensing, cosmology, and astrophysics. He is also well known for his contribution to supercluster galaxies. He is a member of the Indian Astronomical Union, a fellow of the Royal Astronomical Society, and a fellow of the European Astronomical Society. He is widely known for his active role in presenting astronomy to the public, in particular to school students and teachers.
Hello everyone, my name is Rishabh and I'm the admin of the Secrets of the Universe. So before we call Professor Somak Raychaudhury for his talk, I would like to inform all the participants that we would be taking questions after the talk. So I request you all to post your questions in the comment section. So let's welcome Professor Somak Raychaudhury.
Thank you, Shaka and Rishabh. Um, um, Thank you for everybody for joining this evening. I know you have other attractions, but let's talk about cosmology. I'm an astrophysicist, and as you heard, and my subject is cosmology, which is to do with the universe as a whole. So what I want like doing is to put together observations with various kinds of telescopes together to see whether what we can learn about the whole universe, and that's cosmology. And of course, today we're going to talk about what we know. It is very surprising what we can know sitting here on the Earth, not being able to, like other scientists, go to a lab and touch my subjects, or change an experiment and do it again. We are in a unique experiment that is the universe, and all we can do is to learn what we can see about the universe through what the universe gives us, which is different kinds of light, and then we try and figure out where we are, how old the universe is, and today, as I'm going to talk about how we can learn about what will happen to the universe. So let's. I know that there is a diverse audience out there. So I'm going to start from the very basics, and I hope that people who know quite a lot about the subject will have patience with me, and I'll get there eventually. So if you look at the night sky, you look at, for example, here, you can see with the naked eye or the small telescope, the points of light that you see are essentially stars. And the stars all belong to our galaxy. The basic building block of the universe is a galaxy, and the galaxies have lots of stars. We live in one of them, and so we look through that screen of stars to the sky. Now, if you look at, for example, a small part of that night sky, and use a very powerful telescope like the Hubble Space Telescope, you look very far away. Actually, what you see are all galaxies. There are only two stars in this picture, that one and that one. And the others are all galaxies. Each one of them has 10 to the 10, 10 to the 11, power 11 stars. And so that is telling us that if you look far away, you see galaxies. And the fact that there is this distinction between stars and galaxies in the sky was not really known until the 1920s and 1930s. So it's about 100 years we've known this, and this is what makes cosmology and our even knowledge of our own galaxy a very, very new subject indeed. And just to give you a historical sense of where we are, just think about Einstein's theory of relativity coming out in 1915. At that time, Einstein did not know we live in a galaxy, and he did not know the distinction between this picture and that picture if he had these pictures then, right? So this kind of gives us a historical perspective. If you go back to the late 18th century, you will see that these two people were the first people who actually told us about this. William Herschel, working in England, and Charles Messier, working in France, worked a lot on looking through their small telescopes and trying to figure out that there are some stars that are fuzzy, that are nebulous. Herschel called them nebulae. And then they independently made lists of these fuzzy objects in the sky. And we use them even now. If you're an amateur astronomer, you use the Messier list or the NGC list made by William Herschel. And if you look at 4 of these from both their lists made 200 years ago, I can show you modern pictures of them. And they thought they were the same thing. They're fuzzy stars, right? And in this particular list, you have M3, Messier 3, for example, which we now know is a cluster of stars that has 1,000,000 stars in them. Here is M1, which is actually a single star, but it exploded and we see the remnant of it, right? And so it's just a single star, but they look identical through a small telescope on the sky. And here is M27 on the right, which is actually another single star, but it's after it has finished its production of light in the center. It has given off a lot of its mass and it's become nebulous. It's not exploded like the Crab Nebula. And in the middle is M51, which is actually a galaxy which has 10 to the power 11 stars, 10 to the 6 stars, 10 to the power 11 stars, 1 star, 1 star. They all look the same. And they look the same to a small telescope because we don't know how far away they are. And once we know how far away they are, we can figure out what they are. And we did learn how to measure distances properly in the universe till about 100 years ago. And you will see later in the lecture that even then, we could not figure out what's happening in the universe till about 20 years ago, when we really learned how to measure distances to faraway objects, right? So this is the kind of moral of the story, as it were. Let me also give you the answer to the future of the universe. And don't think that I'm going to, at the end of this talk, tell you what's going to happen to the universe. I'll tell you what we know and what we think is going to happen to the universe. But this is a very rapidly moving subject, and nobody pretends that they know, understand the subject to the extent that they can predict what's going to happen to the universe. But what we know is very surprising. And the fact that we can do it is a wonderful story of the challenge taken by scientists and trying to figure out what's happening. So these are galaxies. Galaxies are of 2 kinds. They're nice and round galaxies, which are very old. They're called elliptical galaxies. And there are flat galaxies that rotate very fast, called spiral galaxies, which are about 80% of all galaxies. And about 15% are these nice and round galaxies. And so we live in one of these flat spiral galaxies, right? And these something like this. And this is what our own galaxy looks like. Our own galaxy, this is, of course, can't be a picture because, of course, we can't take a picture of our own galaxy. We live in it. This is an artist's impression. Our galaxy is flat, very flat, and we are offset from the center by about 25,000 light years, 8 kiloparsecs. And we're looking out and we're seeing through the screen of stars, as I showed you. So all the stars we see are in the neighborhood here around the sun, and we are a planet around that sun, right? If you look at the top view of this galaxy, you can see that here's the sun, about 25,000 light years from the center, and we're going around our galaxy like this. And we've been around this galaxy about 20 times in our lifetime. And it's still going around. So and the galaxy is turning very slowly, but the sun is also turning in it. So this is the picture of our neighborhood. Now, if you look at this galaxy and you're looking towards the middle, you will see a band of stars in the sky. And if you're looking in that direction, you see just stars randomly, as we saw in the earlier picture. That band is called the Milky Way, or in Indian languages, we call it the Akash Ganga, the river in the sky. And the Akash Ganga is not very well seen from northern latitudes like in India. Actually, if you go to the southern hemisphere, you see it like this. It's wonderful. This is a picture from northern Chile, a place where I go quite a lot to use their telescopes. Some of the best telescopes are in Chile because it's very dry, and these are high mountains on the Andes Mountains in the Atacama Desert. And you can see in full glory this plane of the Milky Way. And you can see why it is called the Milky Way, and that's the center of our galaxy. These are 2 other galaxies that are our satellite galaxies called the Magellanic Clouds. and they go around our galaxy. There are many, many such. And then if you just go out a little, zoom out a little, you will see that actually we belong to a little group of two large galaxies, our galaxy and the Andromeda Galaxy. You very recently heard a talk in this series by Raja Gotakutta from the University of California. He's one of these experts on the other galaxy we're talking about, the Andromeda Galaxy, and has made many discoveries of these satellites that go around the Andromeda Galaxy. We know, I've shown only a few little satellites here. Our galaxy has about 45 different tiny dwarf galaxies going around. Similarly, the Andromeda Galaxy also has a similar number of tiny galaxies going around, and actually they're falling towards each other. I'll talk about that later. So this is our local neighborhood. Our local neighborhood is such that we have this neighboring galaxy, which is very much like our own galaxy, but it's about 0.7 megaparsecs, which means it's about 2 million light years away from us, and it's coming towards us, and we are bound to each other. So we're going to talk about that later on. Now, galaxies actually collide with each other. So our galaxy is going to collide with Andromeda. I'm going to talk about that later on. Here's a picture of galaxies like our galaxies, for example, M81 and M82. These are nearby galaxies, and you can see that they are interacting with each other. They are pulling each other's material out. The right-hand picture is a picture taken with an optical telescope in visible light that excites our eyes. On the left is a picture taken of the same things, but with a radio telescope. And the radio telescope is sensitive to the cold hydrogen gas that's in the galaxy, whereas the right-hand side, the optical picture, is sensitive to the hot stars that are in the galaxy. So you don't see the interaction between the two galaxies by looking at the optical picture because the stars are not being pulled out, but you can see that the galaxies are pulling out each other's cold gas component, and you can see how they are interacting with each other much more intimately. So this also shows you that in order to do astronomy and study these galaxies that are spread all around the universe, you need to observe in different ways with different kinds of telescopes in different parts of the electromagnetic spectrum. And so that is why we use radio telescopes, which are completely different engineering. They are essentially made by electrical engineers, electronics engineers, the electrical systems. The optical telescopes, which are arrays of lenses and mirrors, which are made by optical astronomers, optical engineers. And then we can have also telescopes that are X-ray telescopes. You can look at X-rays that come from these objects. And these are the detectors there, and the telescopes there are made by people who also do particle physics, high energy photons and things like that. So astronomy brings together a lot of different kinds of expertise to look at what evidence we have from these systems and try and study the universe. And then on the large scale, the distribution of galaxies is very interesting. It's on very large scale. So on the left-hand side, here's a survey called the 2DF survey. It was made 15 years ago, 20 years ago, of galaxies where each point is a galaxy. And there are about 1 million galaxies in this picture. But you can see how on the very large scales, the distribution of galaxies is kind of filamentary, or maybe in sheets where you're seeing cross sections of these sheets, and they're bubble-like. We call it the cosmic web. So that's how the universe is, and we are beginning to understand how galaxies populate the universe and how matter populates the universe. So we now know that the universe started and I'm not going to talk about how we know this because that is a different story. But we now know that the universe actually started at a point. It had a lot of in the history of astronomy, people have thought that the universe is infinitely old, or even not very old at all. Newton believed, for example, the universe is only 5,000 years old, whereas there were other people like Einstein felt that the universe is infinitely old. But now we know that the universe's age is only 13.8 billion years. That is a small number compared to infinite, but a very large number compared to what Newton thought the age of the universe was. And And it has been expanding. So this is what we know, right? And the universe is expanding. It started expanding from a point 13.8 billion years ago, and later when the universe started, it had only energy, and later matter started forming out of that energy, and then stars formed from it and galaxies from it, and now we see the universe like this, which is kind of a filamentary structure of lots and lots of galaxies, right? And this is not a linear map, as you can see that this part of the picture where the universe was still dominated by radiation and matter had not formed is only 300,000 years after the Big Bang. And this to here, which is 13.8 billion years after that, is the history of our galaxies. And we're trying to figure out how, from the radiation, we have the matter that we see now. It's a very, very interesting and challenging subject, by no means sorted out. This is a subject that is very much in its infancy, because what we do is we look at the evidence around us, study the galaxies that are around us, also look at simulations of how such an evolution will happen from radiation to matter, and how matter will interact with each other to form these structures, as you see in galaxies and things like that. So numerical simulations are very important, observations of the universe very important, and different kinds of mathematical models are very important. And so we put them all together and try and figure out what's going to happen. So once we know what has happened in the past, can we fast forward and then see what will happen in the future, right? So that is the kind of story I'm trying to tell today. When this kind of thing became fashionable, a lot of you would have come across Stephen Hawking's book called A Brief History of Time, 1988. In fact, in 1986, when he gave this as a series of lectures, I was present there. I was just starting off as a PhD student at the University of Cambridge when Stephen Hawking gave the lectures, a set of 15 lectures called A Short History of Time, which became this book, which made this subject so popular. It is one of the highest selling books in science. And it became a very, very influential book at that time. Now, actually, if you look at the book now, and if you've read the book, you know that much of the book is not right, because we've discovered a lot of things that Stephen Hawking was worrying about that is not relevant anymore, because they are not in our current understanding of the universe. They don't matter. But it is interesting how he started it off. And what he did was he was talking about how the universe has evolved from the Big Bang to now, and what is going to happen to the future. So this subject of the future of the universe essentially became a very well-known subject outside the small number of people who were worried about cosmology, because people started reading this book as a popular book. And what he was talking about is that coming from the Big Bang, which is a point here, say, and in the past, and then the universe expands, what happens in the future? Does it expand up to a point and then come back? Because that is how all gravitating systems seem to behave. If you throw a stone up in the sky, it slows down, and then it goes to a point, and then it comes back again. If you throw a rocket up with the escape velocity, then it goes and continues forever. It never comes back, which is like this. And whether then there is a possibility where it will not just continue forever, but continue in a way where there is no chance of having a bounded universe in the future. So all kinds of things are possible. And Hawking, in this particular book, talked about all of this. It's a very interesting book. Even though a lot of it is not relevant anymore, it is worth reading just because of the discussions of these possibilities. So this is the three different scenarios he talked about. And of course, he worried a lot about the closed universe and what will happen as the universe slows down. So to actually start all this, to make these measurements, again, I'm going to deal with this in a very, very elementary manner. A lot of you know about all this. How do you study the expanding universe? Let's look at this. So in order to do that, we have to look at the spectrum of light that comes from the galaxies. So as you know, light can be broken up by a grating or a prism into its different parts of the optical spectrum. Just look at the optical part of the optical, meaning the one that the part of the spectrum that we see with our eyes, and it can be broken up into its different components by analyzing a kit like a prism or a grating. Now, in that spectrum, you have various features which can be uh, absorption features or emission features that is related to a particular element. Anybody who's done chemistry knows that it goes into a lab and you can take a Bunsen burner and you can take a potassium salt and it will burn lilac in the flame. And so that's because it's giving out an emission line which is in that part of the spectrum. So here are typical lines that come out of these different elements. And here's a spectrum, say, of a galaxy. And you can see a galaxy, and you can take a galaxy's light and you put it through a grating. You'll see the hydrogen line, H alpha. You will see the magnesium lines, which are in absorption. You will see oxygen lines. You will see other hydrogen lines, etc., and sodium, calcium lines, and things like that. So we know that these things exist in the galaxies, both in its interstellar medium and in the stellar spectra. Now, these lines, we know exactly what their wavelength is. Now, when a source moves and it emits light, its spectrum, the spectrum itself moves in wavelength, right? So for example, if you have the hydrogen line and you have the H alpha line, which is at 656.3 nanometers, which is just here, which comes from every galaxy. Now, if the galaxy is moving and you measure the exact wavelength, you will see that has moved. It's no longer at 656.3, but it moves away. So this is light coming from the Orion Nebula, which is very nearby in our own galaxy, and you can see the H alpha line is still there, very similar. So it hasn't moved much. But if you look at a galaxy that's a little further away, you can see that it has moved. It is no longer at 6563, it's gone to 657. And then a galaxy that is even further, the line has shifted to even more, and so on. So it moves towards the red part of the spectrum, and that's because the light, the wavelength is expanding because the universe is expanding. The idea is that the further a galaxy is, the further its spectrum shifted towards the red. This is called the redshift, and this is how people first started figuring out. And so greater the redshift, and you can see very far away galaxies are very tiny, very small, and the line has moved to something like 658 and nanometers or 660 nanometers or whatever, right? So and further and further and further. And of course, if it's very far away, you will start seeing lights, lines that are in the ultraviolet come into the optical, and optical lines will go into the infrared, and you lose them completely. And this is how you see them. So this is called the method of standard candles. What you have to do is that first of all, you have to measure the redshift, which is the velocity of the galaxy, and then you have to measure the distance, how far away. In here, I'm showing you a sense of the distance of the galaxies by looking at how big they are, right? And so that's kind of as you have a standard ruler, standard size, but all galaxies are not the same size. So actually, if you want to find out how far away a galaxy is, you need a better measure, and that's what is known as a standard candle measure, which is that if you take something for which you know how bright it is intrinsically, like say a 100-watt bulb, you know it is 100 watts, it emits, then you take it at different distances and find out how faint it looks or how bright it looks. You can figure out how far away it is, right? So that's the standard method that we measure distances with. And as I said, the key point here is to know how far away things are, as I started off my talk by saying, and that gives us a measure of the universe. It also tells us about how to measure the expansion of the universe and the past and future of the universe. So very early on, in the early 20th century, this remarkable woman, Henrietta Leavitt, at Harvard, actually Radcliffe College, Harvard University, figured out that there is a standard candle in the way variable stars work. So she identified certain stars called Cepheid variables, which actually pulsate. And so you see their magnitude, which is essentially the brightness, as a function of time. And within 5 days, it brightens up and comes down and so on, like this particular one, right? And she figured out that the period of such a star is related to their actual brightness. So if you measure its period, you can measure its actual brightness, and it becomes a standard candle. And then if you find something, then you know how far away that star is. So that kind of stuff is like gold in astronomy. You actually find a relation in which you can predict how intrinsically bright something is, or how intrinsically large something is. Then that gives you a way of measuring its distance by measuring how large it looks from us or how bright it looks from us. So this man called Edwin Hubble, who was extremely pioneering in this, made these measurements in the 1920s, late 1920s, using partly Henrietta Leavitt's method of finding Cepheid variables in certain galaxies and trying to figure out their distance. He also used spectra to measure how far away these galaxies are moving, how fast these galaxies are moving by measuring their redshift. The redshift tells us how fast the galaxies are moving away from us. And he made this amazing plot. This is Hubble's own plot from 1928. And you can see that he plotted redshift against distance. In this particular case, he's talking about relative brightness, which is a measure of the distance. And it's a very scattered plot. It's not a very good plot because there were large errors in his measurement. But he put a straight line through it and said, look, this tells us that as far away galaxies, the further you go away, they're moving faster and faster and faster. And that's a signature of an expanding universe. You can see in this picture a couple of interesting things. One is that he had 3 galaxies in his sample that are moving at negative velocity, which means they're coming towards us. I already told you one of them. It's the Andromeda galaxy that's actually coming towards us. So, but once you go past a certain distance, all galaxies are moving away from each other. It said, you can conclude that galaxies don't like each other, they're moving away from each other, or they are actually taking part in a general expansion of the universe. So the universe is expanding, and you see pictures like this in textbooks, which kind of try to explain what is happening. This is not a good picture, but you find it in most textbooks. It's like galaxies are embedded in space, and space itself is expanding. This balloon picture is not very good because they can ask the question, who's blowing into that universe? I think this is a better picture in which you think about making a bread, for example, in the oven, and you put some raisins in it or seeds in it. And as the bread expands, you see the raisins themselves are not expanding; they are going away from each other, right? So that's the picture in which you find that the galaxies will all go away from each other. Then you ask the question, why are some galaxies moving towards each other? And that's because these raisins or galaxies are free to move, and locally they can attract each other. And if their attraction can overcome the expansion of the universe, then they're falling towards each other, right? So this is why Andromeda and us, we are falling towards each other, because we are close enough that our gravitational force is very strong, right? So that's the idea. So space itself is expanding, and this causes the light to expand, and so the redshift happens. But and this shows that the universe is expanding. Now, what does it tell us about the past and future of the universe? So if you have the distance of between 2 galaxies now, and then if the universe has been expanding uniformly, which we don't expect, because of course, as the universe expands, there is matter in the universe that should pull it back together, right? But if it expands uniformly, say very, very empty universe, then you can extrapolate back like that and figure out when the Big Bang happened. But if it's actually slowing down, as most people expected till very recently, then you will find that the universe has been going like that. And it's in this particular picture, the slope of this curve tells you how fast the universe is expanding. And so that is going to change and become the expansion rate of the universe is going to become smaller and smaller. And so it will be like that. So actually the age of the universe the Big Bang would have happened even earlier, right? So our measurement of the age of the universe depends not on just measuring the the rate of expansion of the universe now by measuring these redshifts like Hubble measured. We have to also know how it is changing over time. And for that, we need a very precise way of measuring distances. Why is that? In astronomy, we have a very interesting way of looking at the universe. Light that comes towards us from a galaxy very far away takes time, right? So the further a galaxy is, the more time it takes for us to come to us, for the light to come to us. So if we want to know what happens in the very past of the universe, a lot before our current time, we look further and further away. So if you have two galaxies and one is very much further away than the other, then the first one is telling us a lot more about the past of the universe than the other galaxy that's near us, right? Because we are seeing it as it was in the past. So, in order to find out what was there in the past of the universe, we have to look further and further away. And so, if you want to do this and try to figure out what's going to happen, like Hawking said, is it going to go and come back, or is it going to go now? It all depends on us also trying to figure out what happened in the past. And the rest of today, in this particular talk, I'm going to talk about what we know about this, right? And so the question is, you know, whether we know from here, we are here now in the timeline, and in order to figure out what's going to happen here, we need to know what happened in the past. And in particular, as you'll see, we need to know what the universe is made of. These are the two stories that we need to sort out. And this story has not ended yet, but I'll tell you what we now know. So in the 1990s, when I was a student, essentially this was the state of the art. Hawking had written his book, and most of the research was trying to figure out how fast the universe is expanding now at that time, and we were trying to figure out what has happened in the past, and we really had a very lousy measurement of the expansion of the universe even in the 1990s. But one of the important things in this story is to figure out what the universe is made of. And so I digress for a few minutes to talk about the matter in the universe. Now, we know that we are made up of carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These are essentially all the elements, and not just us, but kittens and sweets or whatever, they're all made up of the same thing. We are all made up of elements that are in the periodic table. And the periodic table essentially is made up of the elements there are made up of protons and neutrons, and electrons, and protons and neutrons are made up of quarks. Things that are made up of quarks are called baryons. We are made up of baryons, and everything we see around us, all the stars, the Earth, and all the galaxies that we see that is emitting light, they are baryonic. So is the universe made up of baryons? Is the universe made up of quarks? This is a question that we essentially assumed that is true, except that we got a very rude shock in the 1970s when we realized that that's not true. And this is just to understand that, we have to understand one important thing, and that is, if you, for example, want to measure the mass of the sun in the solar system, what you do is you measure look at the way the planets are going around the sun, and you will see that the further planets are around from the sun, because most of the mass in the solar system is in the sun, the velocity falls off. The velocity falls off like that, right, in the solar system. So that is how you can measure the mass and the matter content of the sun, by looking at all these velocities of the planets. Now, in a galaxy, you can see that that is not true. The sun is probably here in our galaxy, and there is already quite a lot of stars, even up to the distance to us and beyond. So if we go out here, maybe we can measure the total mass of the galaxy and try to figure out how much matter there is. And people try to do that. In the solar system, the velocity falls off, the rotation curve falls off. In the galaxy, you can see that the stars are rotating. And Vera Rubin in the 1970s did this amazing experiment in her master's thesis. She took radio galaxies, the radio observations of galaxies, and took the hydrogen signature that you get, the hydrogen emission line that you measure from a radio telescope outside the galaxies where you don't see any more stars, but you can still see the hydrogen signature, measured their redshifts, and tried to measure how fast they're rotating. And she found that even outside where the stars stop in a galaxy, the velocity doesn't fall down like you see in the solar system. It continues to grow and grow and grow and grow and grow. And she concluded that there must be matter, a lot of matter outside the galaxies, outside the stellar limits of galaxies. This was known as dark matter. So we expected as you went out of a galaxy, the velocity curve will fall, and it doesn't. Vera Rubin's paper actually was rejected by the Astronomical Journal because they said, no, this is nonsense. How can this be, right? And she was a young woman working in the 1970s. It took an older man to repeat the experiment a few years later and find the same result, for that result to become more credible. And then Vera Rubin then is our hero now, because she was the first person to show that galaxies actually have, so galaxies have these lot of matter that is emitting hydrogen outside, and they can be used as test particles. They are not the dark matter, but by looking at their motion, you can see that there's a lot of stuff outside the galaxies that are made up of this matter. And the dark matter dominates the universe, the matter that is not seen, but you can feel it only through its gravitational effect. The stars that you see that emit the light are made up of baryons, and they form a minority in the universe. So this is what we now know. And so galaxies themselves look like this. They are these galaxies like our galaxy, but it is surrounded by a halo of matter, much bigger. In fact, we haven't found a place where a galaxy where the rotation curve actually starts falling. So we don't know the extent to which dark matter is around galaxies. Our galaxy, we don't know where it stops, right? So then you can see, just by looking at the stars in a galaxy, you can't really tell how large the galaxy is or how massive the galaxy is. But we know that there's much more matter in the universe than what you see in the form of stars. And so I showed you that in the local neighborhood, the Milky Way and Andromeda, and they're falling towards each other. Actually, the dark matter around it is probably large like that. And I don't know whether they're even touching, right? Because we haven't found out to these distances the rotation curve falling at all. Okay, so that's the magic of this. So when you try to predict what will happen to the galaxy in the future, you have to include the matter that is around us that you don't see, but you can feel through these dynamical measurements. And people have done that. I did that long time ago and tried to figure out what will happen to these two galaxies as they're coming towards each other. So we've now gone way beyond our sun and our Earth. We're looking at billions of years from now, what will happen to the system of the two galaxies. And I wrote a paper in which I essentially showed that these two galaxies are going to come and merge with each other about 4 billion years from now. And you can see that there's a very nice simulation done by my friend John Dubinsky, if I can play it, which shows this. Why is it not working? Yeah. So this kind of shows, takes the work that we did and does a simulation of two galaxies that are like our galaxy and the Andromeda galaxy, and it shows how in about 4 billion years or so, they will come and collide with each other, and their stars themselves will start merging. The dark matter, these have dark matter that you are not seeing now, but in the simulations they are considered, and the dark matter will make them merge together into a single galaxy. And this whole process will take about 4 billion years. So there you are. So in the end, and then this can go on forever. So this is the future of the two galaxies that are next to each other. Now, this kind of evidence of dark matter you do see from lots and lots of other sources, for example, in clusters of galaxies, where you have not just two galaxies like us and Andromeda, but hundreds and thousands of galaxies. Two, you find that there is a lot of dark matter, not just attached to the galaxies, but in between the galaxies. And this you see by a very interesting method called gravitational lensing. What happens is that if you're asking, do galaxies only contain dark matter, the dark matter around the galaxies? But the idea is that actually dark matter is there also around this cluster of galaxies like this. So what mass does is that it bends light. And so if you have a very far away blue galaxy that you can see, and light coming from it can be bent by this matter, and it comes to us at the Earth observing through a telescope, and this bend can be seen by the fact that you see multiple images of these galaxies in different places, or distorted images of these galaxies. It's called gravitational lensing, as if you because you really the matter itself is distorting the light that's coming to you, and from that you can infer how much matter there is in this galaxy, right? So, for example, if this light is coming from this source coming to you around this galaxy, you can see this galaxy as a ring around that particular galaxy, okay, and things like that. Then, so the lens actually creates all these images, which are multiple images or ring-like images or distorted images. And from the study of that distortion, you can infer how much matter there is. And here's a very famous example, Able 2218 Hubble Space Telescope image of a cluster of galaxies. And you can see all these distorted images of galaxies that are essentially small, tiny galaxies, which are nice and round, but very far away. And they're coming through this cluster, and it's getting distorted into these nice shapes. And in many cases, you see multiple copies of them, that galaxy and galaxy around here. They are the same galaxy, and you're seeing it in different places. That's because you're seeing it like this. You're seeing it because it's coming in two different directions. And from that, you can infer how much matter there is in this cluster. And it turns out there is a few hundred times more matter in this cluster than you would infer from the starlight from these galaxies. So dark matter is a very important in picture. So, but 1995, we were struggling with this idea of figuring out the fact that about 20% or 10% of the matter that we see in the universe is actually the kind of matter that we are made of. And the dark matter, which is not baryonic, which seems to be making up the universe, and that itself was a puzzle. After 95, the whole thing changed because we found a way of measuring distances to very far away galaxies very precisely. And that showed us another problem with our scenario of this universe, which I'm going to talk about as the last part of this talk. So, as I said, initially from the 1980s and 1990s, our understanding of the universe showed us that the universe is expanding, but the expectation was that there's a lot of matter in the universe because we are finding dark matter, which is much more than the matter that we see in the light emitting parts of the universe. And so this matter has gravitation, and as you know what gravitation does, it pulls, it doesn't push, it pulls. And so as the universe expands, you expect the universe to slow down because of the matter that is inside the universe. And so we would expect that it would either come back like that, or it would slow down, and as you go further and further away, it would be like that, right? So this was in the 90s. So the Hubble plot, with better measurement in the 1990s, looked like this. You remember Hubble's own plot was all over the place. This is velocity versus distance, and we're looking at the nearby galaxies, and you can see that this shows that the universe is expanding, but with a particular speed. And the speed of expansion is given by the slope of this curve. As I said, as you go further and further away, you expect that curve, that curve to change, right? And because if you're looking further away, you're looking at the past of the universe. In this particular case, where you're looking at the past of the universe, you would think that as the universe slows down, then it would have been faster. in the past, and now it would be much more slower expansion, and so you expect the slope of this to change in the past, which means further away. So here you are. The question is, so the Hubble expansion cannot be a straight line. This thing cannot go on forever because the expansion rate of the universe has to change. So the idea is that you need standard candles. In the mid 90s, a fantastic standard candle was found, and that is the fact that you can have a type of supernova called type 1a supernova in outside galaxies, in other galaxies. These are very bright objects because as a star explodes to form a supernova, it can outshine the galaxy. This is a similar supernova that happened in 1987 in our neighboring galaxy, a satellite galaxy that's the Large Magellanic Clouds, and you can see for a month it looked like that. If something like that happens in our neighborhood, like it happened for the Crab Nebula in 1054 AD, you would see two suns in the sky for a month. Actually, that's what happened in 1054. You could see a second sun in the sky. And similarly, if you look at other galaxies, you can see these things, and these things explode. And so in the 1990s, we learned that how to read the wattage label on these supernovae, which means that they became standard candles, like the Cepheid variables. Once that was discovered, then all these surveys started to put different parts of the sky. There are big telescopes that would look at the same part of the sky every night, and suddenly find one of these supernova happening on one of these galaxies. And then once they are found, you had to wait till it became the brightest. The whole thing takes about a month and then fall down. And it's the peak of that supernova that is the standard candle, it will tell you. And then you have to identify it as a type 1 supernova, type 1a, which is actually the kind of supernova in which the whole star explodes. And as opposed to the other kind of supernova, which is type 2 supernova, in which the outer part of the star explodes, the inner part implodes to form a neutron star or a black hole. So the type 1a supernovae are the kinds in which the entire star explodes, and that leads to this nature of it being a standard candle. So this was identified. Of course, it led to a Nobel Prize. And so, for example, this telescope that I showed you in this particular picture, the Blanco telescope in Cerro Tololo, which I showed you when I talked about the Milky Way, it's the same telescope. It's now used as a dedicated telescope to find these supernovae. It's called the Dark Energy Telescope, and in Chile. And there are many such telescopes that do this. And so here I give you an example. For example, here is a picture taken by the Blanco telescope on one night, and here's one 3 weeks later. It takes pictures every night, and you can see it is very difficult to see with the naked eye what's happened here. But if you digitally subtract one from the other, as is being done, you can see that in this particular galaxy, a supernova has appeared, right? You subtract one from the other, and then once that is discovered, soon you send the Hubble Space Telescope to look at it, and you can easily see that outskirts of the galaxy these supernovas happened. You take a spectrum, you identify it as a supernova, and it becomes a standard candle. And once that is done, this is what happens. So Hubble's plot in 1928-29 looked like this, if you remember, of redshift versus distance. The same plot in 95, before the supernovae were identified as a great distance indicator. The best ones used Cepheid variables and things that depended on Cepheid variables. And you can see that it's still the Hubble plot, which tells you the expansion rate of the universe is still very straight. It hasn't curved yet. And that real yellow blob is what Hubble's entire sample was. You can see it went out to about 10, 15 megaparsecs. It's out there. And you can see even in 95, we could go very far away, a few hundred megaparsecs, and it hadn't really curved much. But after these supernovae were found, then that entire plot, this goes into this yellow blob here, and the new measurements of supernovae show that this Hubble plot now, which is the velocity versus redshift relative distance plot, has now curved in this direction. Now, this is a big surprise. That is because if the universe was slowing down, then in the past, the expansion rate would have been much higher, and now it's lower, right? So because the slope of this curve shows that, one expected this curve to go like that, right? It curved like that because the slope of the curve would be much steeper in the past, i.e. further away. And the measurements with the supernovae showed us that the universe was actually much slower expanding in the past, and now it's faster. Now, that is totally counterintuitive, because if the universe is made up of matter and matter gravitates, it has to pull things together. So we now know that the universe is actually speeding up. It is not slowing down, right? So you remember the plot as we showed. If you're taking this now, and if the universe is slowing down, then it would behave in a certain way. But now we know that it's going like that. And so we can figure out what the age of the universe was, but also figure out what's going to happen in the future. So we now know, for example, that the universe is made up of something that pushes, not pulls. It is not matter as we know it. It doesn't gravitate. So we know that 70% of the total mass energy of the universe is this mysterious thing that pushes, doesn't pull. And it's called dark energy, which is not a good name for it, but that's what it is called. It makes the universe accelerate. And the rest, which is about 30%, is matter, which gravitates, out of which 25% is this dark matter. And only 5% of the universe is made up of what we are made of, which is the baryons. And that is the big surprise about the universe. So what is going to happen to our universe? The implications of dark energy is that normally it would have decelerated, but it's accelerating. So you remember Hawking's famous picture of the universe coming back upon itself, the closed universe. That is not going to happen. That is a lot of the discussion in Hawking's book was about what is going to happen when the universe comes back. And it won't, because the universe is accelerating. It is becoming larger and larger and larger. And in the end, what is going to happen, it's going to end in a big rip of the universe, which means that as it accelerates, it is going to become larger and larger and larger. The distance between the galaxies are going to become very, 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 very large. And space-time itself is going to go towards something that is extremely large. Now, this is what we think now. We don't know. I mean, I told you when I was a student, we had a completely different view of the universe. And this changed with our knowledge of what is happening at very large distances by measuring the distances of galaxies and looking at the Hubble plot. I'm hoping that in the generation of the younger people here, this is going to be understood. We don't understand dark matter. We don't understand this dark energy in physical terms yet. And so we don't know really, if this is the future of the universe. But this is what we now think is the future of the universe. I'll stop there. Thank you. And see whether there are questions.
Thank you so much, sir, for such a mesmerizing lecture. And never thought that the ending of a universe could be such a complex event. And your presentation was a rare combination of scientific topics articulated in a clear and engaging manner. And I was particularly fascinated by how do we study the expansion of universe. I heard a lot of talk about it, but never knew that a simple concept like dispersion of light is at the center, which enables us to study it. So thank you so much, sir. So we'll be taking the live questions now. Over to you, Rishi. Thank you.
Thank you so much, sir. And the best part of the talk was when you said that to study the future, we have to study the past also. So that was a really insightful thing for people who are interested in studying astronomy. So we'll begin with the questions.
Can
The
I take
first
out the
question.
slides? Shall I just stop sharing and just see so that, yeah, I'll take out the slides. Yeah, you
Yeah.
can give the
Yes.
question. Thanks.
Okay. So the first question is by Mohammed Said. Sir, can you please explain how is it possible that the universe started from a simple point and then expanded for 13.8 billion years with so many galaxies and stars?
Yeah, so, I mean, um, how do I know? I don't know what was there before because we will never know, right? And but the way we understand that the universe started from a point is by doing what I just said, by kind of playing back the film. You can see how the universe is changing now. It is expanding and the galaxies are moving away from each other. So then you reverse it and then see what happens. And as the universe expands, you saw how precisely we've measured the rate of change of the rate of the expansion of the universe. We play that movie backwards, as it were. And you will see all these galaxies will come together and become one at one point, right? And the person who actually solved this Einstein's equation to actually tell us this was a remarkable person called Father Lemaitre, Joe Lemaitre, who was a mathematician working with Einstein in the 1920s. And he solved Einstein's equations to show that if you take the general relativity equations, that's what it says. It's either going to, space-time is going to expand or contract, but it's not going to stand still. And then he worked out this and said, look, even before Hubble had made those measurements, he said, this is the universe has to expand and keep going. And in the past, it came from a point, and he called it the cosmic egg. And so we don't know what that egg looked like. We don't know what that point looked like. But we know that just by looking at extrapolating into the past, that the universe would have started from a point. And 13 billion years is where we are now. It took us so long for humans to evolve on a planet to look at the universe. We don't know whether there are other planets in which other people have evolved to look through their telescopes and say 11 billion years after the Big Bang to come to this conclusion saying, oh, the universe is 11 billion years old. But on this particular planet, it has taken us so long to evolve and evolve a brain and evolve technology to look at the universe and say, look, I can measure the age of the universe. It has taken us so long. That's why it is 13.8 billion years old, because we are here now. We didn't know this, 30 years ago.
That's really great, sir.
Okay. So the second question, sir, is from Roshita. Her question is, what is cosmology and how is it useful in our everyday life?
It's a very good question. Cosmology, of course, as I said, is the study, just like geography is the study of the Earth. Cosmography or cosmology is the study of the universe as a whole, of the cosmos. And so we are talking about the biggest questions there are. We are looking at the universe as a whole, not individual stars or galaxies, but the universe, and looking at the nature of space, nature of time, and answering questions like asking questions like this: how old it is, how fast it is moving, etc., etc. So that's cosmology. What is it used in daily life is a very interesting question, and that is, I mean, in order to make these measurements that I talked about, one has to learn a subject and develop instrumentation in order to get there. And that means that you push technology, right? So, for example, the entire subject of physics came from a single question about an astronomical object. Halley came and asked Newton, why does this comet come back every 75 years? And Newton started thinking about it and put together the Newton's laws of motion that we study in school and the gravitational motion, and then found that there are these elliptical orbits that comets could make comets go around the sun, right? So if you ask the right question, you get an answer, but then something happens. A whole subject starts. The whole subject of physics came from this single question. Similarly, I showed you the measurement of the redshifts of galaxies, right? As and finding the Hubble expansion of the universe, right? The modern measurements come from the Hubble Space Telescope. It's called the Hubble Space Telescope because it was sent up to measure this. Now, when the Hubble Space Telescope was sent up, people said, how are we going to develop photographs that the space telescope will take? It has to send us back. When I was young, you took them to a shop, and then they took the film and developed it into pictures. So that is why a digital camera was invented. So you have a phone in your pocket, it has a camera, it was invented for cosmology, right? To make that picture. Right. So that is only one example of what cosmology has given you in daily life. Almost everything in your phone, actually. In fact, the phone communication comes from the development of radio astronomy. The kind of radio astronomy I'm talking about, it started with development of radars in the Second World War, and then radio astronomy. Radio astronomy started developing these very, very sophisticated communication systems with radio, which evolved into the mobile phone that you have, right? The GPS system comes from this work. Now, in the GPS system, you ask your phone where you are right now, and the answer that you get depends on our knowledge of the nature of space-time around the Earth. In fact, you used Einstein's general theory of relativity in that calculation. The same general theory of relativity that is giving you the expanding universe gives you the exact time taken for the signal to go to a satellite, 3 satellites, and come back to your mobile phone, and it tells you exactly where you are. If you did not use Einstein's general theory of relativity, you would have the answer wrong by 10 kilometers, right? So the phone tells you where you are because somebody asked the right question, which led to a cosmological question, but also led to your mobile phone. So and I could go on. I could give a whole lecture on this. But the thing is, in science is all connected. And so when you ask a smart question, and then you have to invent things to make that measurement, to give the answer to that question, that goes on and creates something else. It makes your life better. And in daily life, we have many, many such examples of things that have come out of astronomy.
Great.
I'll stop there.
That was really great, sir. That was really great because when people used to ask me what's cosmology used for in real life, I didn't have an answer. Now I have one. So the
Well, I
next
can give another
question.
example. I mean, MRI, right? You go and do these see CAT scans or MRI scans. They came from studying galaxies. You try to figure out how a galaxy is done, is in three-dimensional way, how the disk is and bulges, etc. And the astronomer who figured that out also invented CAT and MRIs, right? So there are so many examples I can give you that come from measurements of astronomy. Anyway, go ahead, ask other questions.
Okay, sir. The next question is my question. So my question is that when we say the universe is 13.8 billion years old, is it only from our frame of reference? Because time and space are relative and they change in different gravitational potentials. So suppose someone is studying the universe from another planet or on a planet near a black hole, the time would be very different over there. So how do these two things how
Very
do
good
we
question. And the answer is actually in the universe there is an absolute frame, and that is the universe itself. And when I say 13.58 billion years, it is measured in that frame, not in my frame. Okay, and that is we can do that because I didn't talk about the cosmic microwave background today at all, but it is a radiation that you can measure, which is left over from the Big Bang. Okay? And this was discovered in the 1960s. It has led to 2 Nobel Prizes. And the cosmic microwave background is the radiation that is left over from the radiation that the universe had at the Big Bang. And much of it has been transformed into matter, but there's a lot left over as radiation, as photons. And as the universe expands, this thing cools. At the beginning, the universe was very, very hot. But now, the universe is so large, this thing has cooled to a temperature of 2.7 degrees Kelvin, right? So minus 270 degrees Celsius. So the temperature of the universe is 2.7 degrees Kelvin. And this cosmic and it emits mostly in the microwaves, because if you take a black body curve, it peaks in the microwaves. So this was measured in the microwave, and you can measure it, and you can measure it all the way around. Anywhere you point your microwave telescope, you can measure it. And so this, and then that becomes the rest frame of the universe because it's tied to the universe. It is expanding with the universe. And we are moving with respect to it. Right? So we are moving around the sun is moving in the galaxy is moving around Andromeda and our galaxy is moving. So all of these are moving with respect to this frame. And when we make these measurements, we describe it or we publish it in terms of a velocity, or all velocities or times are measured with respect to this frame of the cosmic microwave background, which is the universal frame. But you're absolutely right. If I did it with respect to me, I'll get a different answer. If you are near a very massive star or a black hole, you'll get a different answer. Right?
Thank you so much, sir.
Okay, so the next question is from Devang, and I feel that this question most of us we have. What was there before the Big Bang?
So that is a very good question, but not only do I not know the answer to it, I will never know the answer to it. I can only speculate, right? So because before the Big Bang, there is no information coming to us from then. Yeah,
Yes.
we can only get information. In fact, we don't even get information from the Big Bang because the universe, as it expands for the first 300,000 years, it was opaque. Light couldn't get through because it was in a very, very dense state. And suddenly it became transparent. So I can see photons coming from that time. But before the Big Bang, there is no information that can ever come. In fact, there can be gravitational waves coming from the Big Bang to us when we can detect it. And so we will never know. And thus, this is a very philosophical question. Can you essentially ask a question to which you will never know the answer? Bishop Berkeley posed a very important question in philosophy 300 years ago and said, look, you go outside the room and you come back and you see the chair is there, same place that you left it. But do you know whether the chair danced around the whole room and then came and sat there? You will never know. You,
Correct.
through your knowledge of reality, you make this connection that you know chairs don't dance. Right? And that is why you can say, look, I left the chair there and it is still there, so nothing happened. Similarly, there are certain questions to which there is no answer. So you cannot ask, you can only infer. Okay. So questions like what is outside this universe? People say there are many other universes. What is before this universe? We will never know. Now, having said that, that doesn't stop people from imagining. So there are many theories. There are wonderful theories in which people think that there are many Big Bangs serially. So, for example, this universe in the future will just disperse and become a very large place. And then maybe there'll be a bang somewhere, and another universe will start. Right? And so maybe universes come from previous universes. You can ask the question, where does all the energy in the universe come from? Maybe it came from a previous universe. Maybe there are millions of universes all coexisting with each other, and they collide with each other, and they form other universes. These are wonderful theories. And actually, there's a wonderful book called The Mathematical Universe, which you can find, it's very easily available, which actually discusses all these possibilities. They're lovely, kind of theoretical ideas of what's outside the universe, the multiverse theory, what's before the universe, what's after the universe, and things like that. And these are all kind of speculations which will never be, proved or disproved, but it's fun to think about.
Correct. The curious human brain. I mean, they'll always be asking such questions. So you said the mathematical universe, the book that you
Max
talked about.
Tegmark is the author. The author is Max Tegmark, and
Okay.
Mathematical Universe. It's
So
it's
so
a
there
wonderful book.
there must be a lot of equations in it. So what is your favorite physics equation? If I talk about favorite, something that you love to work upon.
Well, I mean, actually, the, the simple equations are wonderful equations. I think the simple equation that we grew up learning in school is force is the gravitational force between two objects, m1 m2 g over r squared. That seems to explain almost everything. Other than, of course, when you go near black holes or you travel very fast compared to the speed of light, and then you have to make a correction that Einstein gave you. If you want mathematical complexity, you should look at Einstein's way of looking at gravity. That's the general theory of relativity. It just gives you wonderful, and we haven't explored the whole thing yet. But to me, almost everything I do, I can do by Newton's that simple equation, which goes, so, it says that the force is proportional to 1 over r squared and proportional to the mass of the object. And that's a lovely thing that Newton came up with sitting under this apple tree, when he was 21 years old. And it's my favorite equation, I think. It's also very interesting, I mean, I don't know whether you know the story of how Newton got this equation. It was exactly the same as the current situation in a pandemic. Newton's University, Cambridge, had closed because of the plague for 18 months, exactly the same as now. So they all had to go away from university, and Newton was a third year undergraduate at that time.
Yes.
And he went to live with his aunt because his mother lived very far away and didn't want him to come to her. So he went to live with his aunt, and his aunt had this lovely apple orchard with lots of apple trees, and he used to sit under that and do his own work. And he discovered differential calculus during that time. This is a third year undergraduate. He came across essentially the result, which is the binomial theorem, and he worked out the universal law of gravitation. He realized that you could actually create closed orbits, and if you assume that there's a universal law of gravitation between two objects. So it's interesting that I don't know how many of the people who are listening to this during this pandemic period have made such discoveries. They still don't know. They might have, if they've been working out, looking at nature. It would be wonderful. This is a good kind of positive thing that a lockdown can give us. You can go and start thinking about such things.
Like, a lot of people have taken a lot of interest in astronomy as a whole, due to the clear skies during the pandemic. That's all I can say,
That's
because we have
also
seen the numbers increasing like anything. The curiosity around this, and among the children, it's rustic. We have to really look through the numbers that it has risen up. Okay, so I think we have the last question, Rishabh.
So then the last question is that when two galaxies merge with each other, do their individual stars also collide during the process?
very, very good question. I mean, I did not talk about it. That's a whole subject of its own, but no, the answer is no. And that is because the size of the stars is very small compared to the distance between them. When galaxies collide, essentially, if there was nothing else other than stars, the stars would go right through, because the stars themselves are tiny, and from the distance between the sun, for example, and the nearest star is 4 light years. It's a huge distance, right? What actually collides is that in between the stars in the galaxy, there's the interstellar medium, which has gas, cold gas, hot gas, gas that is 10 degrees, 100 degrees, 1,000 degrees, 10,000 degrees hot, different kinds of gas. And there's also dust. And so this is a continuous medium. So what you saw in the simulation that I showed was that as the galaxies are colliding, it's that interstellar medium, which is the continuous medium, that collides and sticks to each other. And the stars go right through. So actually, when we are going to collide with Andromeda, it might happen that the solar system will be unscathed completely, right? Certainly, the sun is not going to, very unlikely, is going to hit another star. And
But
so,
sir, is it possible? Yeah.
go ahead. Yeah.
Is it possible that two stars may form a binary system because they
Yes,
were
so
whizzing
that
past each
happens
other?
all the time. But also, stereo collisions happen. I mean, I'm not saying that it doesn't happen. For example, all the LIGO sources that you're seeing are essentially black holes hitting each other and merging, right? So what happens is that first they form a binary, they go around each other, and they spiral in and then merge, right? And that emits gravitational waves, which LIGO has been detecting, and they've detected 50 such sources. So such things happen, but there are billions and billions of such stars. And what happens is that if two stars come very close, they capture each other gravitationally and they form a binary system. More than half of the stars in our galaxy are in binary systems, right? Our star is an exception to some extent. Most planets should have two suns in the sky. because they are binary systems, and they are binaries, and the binaries also then break up, like human binaries. They, people get together, they break up, and they have some other star that they form a binary with, and so on and so forth. And this is happening all through the galaxy. And so they happen, and the binary system can be such that they go around each other for a billion years without even coming very close and hitting each other. So stars forming a binary system does not mean that they're going to collide, right? Because angular momentum is cannot be destroyed. So as stars come very near each other, they go around each other because they have that angular momentum, right? In the case of black holes, that angular momentum can be destroyed by the intense gravity, and that is why they can merge. But normal stars don't. So binary systems are very stable without the stars themselves colliding. So stellar collision is a very rare process.
Thank you very much, sir. So that was the end of the question answers. I, on behalf of the Secrets of the Universe and Gurukul Academy, I extend a very hearty gratitude to Professor Somak Raychaudhury for accepting the invitation and sharing with us his valuable thoughts about the future of the universe. Your thoughts have enlightened our minds and have shown us a new path. Your rich experience in public service and leadership is a shining example for the youth of the nation who are watching us today. We also thank the Physics Club of Aizer Behrampur 137 Inverse for their support. Finally, I would like to thank all of you for joining us from different parts of the world. It is your love and support that keeps us going and inspires us to continue our work. Stay tuned to our channel for many more such talks in the coming Saturdays. Thank you.
Thank you so much, sir. Thank you so much for joining today.